Good day everyone. Topic covered in Chapter 6 is the two-port networks. However, in this video, I will only show the first part of this topic, that is the impedance parameter, or Z parameter. Let us begin. These are the learning objectives of Chapter 6. First, you should be able to define what the two-port network is. Second objective is to describe the parameters that are used to represent the two-port networks. Altogether, there are 4 parameters that you will learn in this topic. But in this video, only Z parameter is described. The final learning objective of this topic is able to analyze the two-port network when it is connected in series or parallel, or when it is connected to any one-port network. Before we proceed with Z parameter, first we need to recognize the type of network. This is a one-port network. In this type of network, the access to the network comprises of 2 terminals. Whereas in a two-port network, as seen here, there are 2 separate ports, namely the input port and the output port. We use a two-port parameter to describe a two-port network by using the voltages and currents at the input and output ports. The labels of these voltages and currents are important when analyzing such network. The two-port networks exist in many applications, such as in the communication field. For example, a communication system between Batu Pahat town and Parit Raja. It has 2 ports, one at each location. Even though we do not have prior knowledge of the internal circuitry of this system, we are still able to describe and analyze it based on the voltages and currents of the ports, thanks to the two-port parameters that represent the network. One of the benefits of using two-port network. Another benefit of two-port networks is the circuits can be represented by their terminals variables, which are the voltages and currents values. This makes the analysis of the system easy and less complex. In many cases, the internal circuitry of a network is not needed as long as the parameters describing current I1 and voltage V1 of the input port, also the current I2 and the voltage V2 of the output port are available. Impedance parameter, or Z parameter. It is the parameter that provides the description of a two-port network in the form of impedance values. This is the matrix equation of the impedance parameter that relates the voltages and currents of port 1 and port 2. By expanding it, we get 2 equations. Set the current I2 to 0 ampere, then we get Z11 as the ratio of voltage V1 to current I1. Hence, it is known as the input port impedance. At the same time, the Z21 is obtained as the ratio of voltage V2 to current I1. This parameter is defined as the transfer impedance from port 2 to port 1. Then, by letting the current I1 to 0 ampere, we can get Z12 and Z22. Z12, which is defined as the transfer impedance from port 1 to port 2. Z22 is the ratio of voltage V2 to current I2, and it is known as the output port impedance. The circuit here is used to represent the two-port network when the impedance parameter is used. It consists of the dependent voltages, which their values transfer impedances Z1 to 2 and Z21 at port 1 and port 2, respectively. When a two-port network consists no dependent source, the network is a reciprocal type. For impedance parameter, when Z12 equals Z21, then we know that it represents the reciprocal network. What is meant with reciprocal network? When the network is said to be reciprocal, the voltage and ammeter at port 1 and port 2 are interchangeable as illustrated here. We can use the T network to represent the reciprocal two-port network. The impedance of port 1 branch is the difference between Z11 and Z12, while the impedance of port 2 branch is the difference between Z22 and Z12. The middle branch is the transfer impedance, Z12. The table here shows the steps in obtaining the impedance parameter of any two-port network. We divide it into 2 parts. Part 1. Find the Z11 and Z21, that is, we set the current I2 to 0 ampere. Simply connect a voltage source at port 1 and open circuit port 2. Draw the circuit and label all the variables. Then, analyze the circuit to find the expressions of I1, V1, and V2 so that we can compute Z11 and Z21. Then, we proceed with part 2. Here, we find Z12 and Z22. For this part, a voltage source V2 is added at port 2 and port 1 is left open circuit. Draw the circuit and label the variables. Do the analysis of the circuit to determine V1, I2, and V2. Finally, we can calculate the Z12 and Z22. Let us see one example on how to apply the method. Example 1. We are required to find the impedance parameter of a circuit, shown in figure E1. The circuit consists of dependent current source that rely on the current I of this branch. So how are we going to obtain the impedance parameter of this two-port network? Based on the equations of impedance parameter, by setting the current I2 to 0 ampere, we can obtain Z11 and Z21. So this is what we do. Connect a voltage source at port 1 and open circuit port 2. Draw the circuit and make sure all the variables are labeled correctly. Then, we analyze the circuit. First, apply Ohm's law to this branch. The voltage V2 equals I multiply 4 minus J2. Name this as equation 1. Then, again, we use Ohm's law to obtain the current flows through the 1 ohm resistor. Its current is an addition of 2I and I, while the voltage across this resistor is the difference between V1 and V2. Name this as equation 2. Substitute equation 1 into equation 2, we get the expression of V1 in terms of current I. Call this as equation 3. Next, apply KCL at node 1, which is here. We obtain the expression of I1 in terms of V1 and I. Therefore, we substitute equation 3 into this to get rid of V1. I1 equals I multiply 3.5 minus J 0.9 ampere. Now, we have expressed the variables I1, V1, and V2 in terms of I. Then, it is time to compute Z11 and Z21. Z11 is the ratio of V1 to I1. The current I is cancelled off, we get Z11 equals 2.014 minus J 0.054 ohms. Meanwhile Z21, which is the ratio of V2 to I1, is equal to 1.21 minus J 0.26 ohms. Now we proceed with part 2, that is to find the Z12 and Z22. Set the current I1 to 0 ampere. We open circuit port 1 and connect a voltage source at port 2. Draw the circuit and label all the variables. The two-port network is now ready to be analyzed. First, apply Ohm's law to this branch. The voltage V2 equals I multiply 4 minus J2. Name this as equation 1. Next, apply KCL at node 2, which is at this point. We obtain the expression of I2 in terms of V2 and current I. Substitute equation 1 into this to remove V1 variable. Here, current I2 equals I multiply 3.23 minus J 0.525 ampere. Then, use voltage divider to obtain voltage V1. Substitute equation 1 into this, we get the expression of voltage V1 in terms of current I. That is V1 equals I multiply 3.77 minus J 1.475 volt. Now, we have expressed variables V1, I2, and V2 in terms of current I. The next step is to compute Z12 and Z22. Z12 is the ratio of voltage V1 to current I2. The current I is cancelled off. We get Z12 equals 1.209 minus J 0.26 ohms. Meanwhile Z22, which is the ratio of voltage V2 to current I2, is equal to 1.305 minus J 0.407 ohms. We have determined all the elements of impedance parameter that represents the circuit of figure E1. Example 2. In this question, you are required to draw the circuit that represented by the given impedance parameter. How to obtain the components that constitute this two-port parameter? The answer for question can be obtained easily. Notice that the Z12 and Z21 are of the same value, that is 1 minus J1 ohms. This indicates that the network is reciprocal. Hence, the T-network is used to correctly represent the circuit. The impedance at port 1 branch is the difference between Z11 and Z12, while the impedance at port 2 branch is the difference between Z22 and Z12. Once all values are obtained, we draw the circuit clearly by indicating the components' values. If it is not a reciprocal network, then you need to use the circuit comprises of two dependent voltage sources with transfer impedance. Example 3. This is the final example. Here, we want to find the supply voltage Vs that will produce the voltage across the load to 5 volts. Figure E3 clearly shows the two-port network that is connected to other components at both ports. Although no internal circuitry of two-port network is given, we still be able to find Vs. This is because the impedance parameter that describe the network is provided. Always remember to draw the circuit and label all the variables, especially the voltages and currents, of port 1 and port 2. Now, we can analyze the circuit. First, write the equations of impedance parameter. Substitute the parameter values into these equations, and name the equations accordingly. From the circuit, we can see that Vs equals V1. Meanwhile, at the load, RL, we can calculate the current I2 by using Ohm's law. Its value is equals to minus 2.5 amperes. Then, voltage V2 can be found by multiplying I2 and 6 ohms. Therefore, voltage V2 is equivalent to 15 volts. Next, substitute I2 and V2 values into equation 2 to obtain the value of I1. From the calculation, I1 is 22.5 amperes. Now, we can calculate voltage V1 by substituting the values of I1 and I2 into equation 1. Finally, we find that Vs equals to 107.5 volts. From this example, we see that the two-port network has enabled us to analyze the circuit without knowing the whole composition of the system. Not only that, the two-port network also makes the analysis simpler. In this video, we have gone through some examples on the impedance parameter. I hope that you will be able to apply the impedance parameter in solving the two-port network problems. That's all for this video. Thank you for watching.